Okay, so last time we discussed the Green's function, and we saw that the necessary and sufficient condition for the Green's function to exist was that there is no zero mode. Okay, so in other words, I mean, if I am given a Lx operator, so there should, if there is no solution to this equation which satisfies the boundary conditions, then Green's function exists. Okay, and it is unique. So if this U is supposed to satisfy two boundary conditions, yeah. So if there is no solution, to this combined equations, I mean this equation together with the boundary conditions, then Green's function exists. Then this implies Green's function exists and is unique. Yeah. Actually, it is also other way around, because we also saw that this is a necessary condition for the Green's function to exist. So it's both ways. Yeah. Okay, now let's discuss the situation where actually there exists some zero mode. What can we do in that case? So suppose zero mode exists. Suppose there is a solution. There is one or more solutions, whatever. There is some solutions. We satisfy both this equation and the boundary conditions. Of course, in this particular, in the second order differential equation, we know that at most there can be two zero modes, because anyway there are only two linearly independent solutions, right? So there can be at most, so either one or two zero modes might be there. So that depends on the kind of equations you're talking about and the kind of boundary conditions you're imposing, right? Sometimes you can have zero modes. Okay. So under that case, in that case, what can we do? How can we solve some equation like this? I mean, say we are given an equation like this, Lxu equal to f, and let's suppose there is some solution u naught to this equation. In fact, let me label it by ui, because it could be, there could be even two zero modes, right? So ui, I could be just one value or two, depending on the number of zero modes. So first of all, I mean, so how can we solve this equation? That's the question. After all, Green's function was a tool that we were using to solve an equation like that, right? I mean, so once you find the Green's function, then you can just find the solution for u, right? So let me again remind you. So what was the use of Green's function? The main use of the Green's function was to be able to solve such equations. Because the Green's function satisfies this equation, g xy is equal to delta x minus y over wx. So then I can find a solution. Once I find what is Green's function, then a solution to this equation is simply dx wx gxy times gxy dy wy and f of y, right? This solves the equation. So that is the purpose of the Green's function. Okay, but in any case, so our main aim is to be able to solve such an equation, right? Now, first of all, one can see that actually this equation may not have any solution at all. Okay, and I will say the reason. Now, consider the adjoint equation, L dagger xv equal to 0, this equation, together with the adjoint boundary condition, whatever the adjoint boundary conditions are, b1 tilde v equal to b2 tilde v equal to 0. So I'm always at the moment talking about homogeneous boundary conditions. Later on I will extend to inhomogeneous also, but for the moment it's all homogeneous boundary conditions. So suppose this has some zero mode. The adjoint operator has some zero mode. So suppose there are some zero modes. Suppose this has some zero modes, which I again label by Vi. Okay, so say there is some zero mode. So, yeah. Then let's consider this equation and let's take the scalar product of this both sides with Vi. So let's take the scalar product of both sides. So what we will find from this equation, so from here, I just apply scalar product. So Vi bar x dx wx, and then you have Lx u. That from the, on the right hand side you will get this is equal to dx wx v bar ix fx, right? I mean, so I'm saying that take suppose that there is some u which satisfies this equation. Okay, I then take both sides of this equation. I take the scalar product with vi. So you get that. Okay. On the other hand, this quantity is the same as dx wx u L dagger x vi whole thing bar, right, by Green's identity. Okay. On the other hand, we are saying that L dagger x acting on vi is 0. I mean, this vi is a solution of this equation subject to these boundary conditions. Remember, Green's identity says that this is equal to that provided u satisfies this boundary condition and the v satisfies that joint boundary condition. Okay. Otherwise there would be surface terms, right? So the fact that I am writing this, I am already assuming that u satisfies this boundary condition and v satisfies that boundary condition. Okay. So the surface terms drop out, and then this is equal to that. Okay. But this is 0, right, because vi was precisely the solution of this equation. So this is 0. So left hand side is 0, right? So right hand side better be also 0, otherwise there is an inconsistency, right? So this must be equal to 0. So what this is telling you is that I cannot just find a solution to this equation for arbitrary f. Okay, f must be orthogonal to the 0 modes of the L dagger operator, right? So only then you can hope to find a solution. So this implies that f is orthogonal in the sense of the scalar product, orthogonal to all the vi 0 modes. These are the 0 modes. Okay. So this is a necessary condition for the solution to exist of this equation. But this argument also tells you, explains to you why there is no Green's function in this case. You see, I mean, in fact, we already know it, but from this point of view, you can see it more clearly why there is no Green's function, because the Green's function equation is Lx of gxy is equal to delta x minus y divided by wx, right? The point is that, I mean, after all, this equation is essentially the same as that. There is an inhomogeneous term. Instead of f, you have this delta function, right? So it's again an inhomogeneous equation, right? Except the right hand side is not an arbitrary function, it's a Dirac delta function divided by the weight function. Okay? But the point here is we have already seen that a solution can exist only if this f is orthogonal to vi. That means that so this solution could exist only if this was orthogonal to vi, right? But let us just check what do we get if we just take this object and integrate dx wx vi bar times f, where f is now this one. So delta x, so this is x minus y divided by wx. Well, wx cancels, and you find that this is nothing else but v bar I at y, yeah, which is not 0. I mean, if there is a 0 mode, this is obviously not 0, right? So this is not orthogonal to the 0 modes of the L dagger operator, and that's the reason why we are not able to find the Green's function. Okay, so now this also suggests how you can find a generalized, how we can define a generalized Green's function. Okay, so what we want to do is replace the right hand side by something which is orthogonal to all the 0 modes of the L dagger operator, and then you can see what one should do. Basically, one has to just subtract from this vi x. So let me do the following. I will normalize the VIs. So we can always normalize the VIs, okay, such that its length square is 1, and orthogonal. If there is more than one 0 mode, I can choose an orthonormal basis, okay, with respect to this norm with the W. So in other words, I can always do this dx. I can choose the V's in such a way that dx Wx Vi bar x Vj x is equal to delta Ij. So I can do that. I mean, in fact, in this case, it's maximum. There can be only 2 0 modes, right? So, well, in the two-dimensional space, you can always orthonormalize it, right? Typically, actually, you will get only 1 0 mode, if at all. Typically, not 2. In that case, there will be just 1 0 mode, and you just have to normalize it to 1, right? Whatever the length, whatever. If this was not 0, you just divide by the square root of that number to make it length 1. That's just for simplicity. It's not. Okay. So consider this V I. I think there's a misprint in this in the notes. I will check now. In this in the notes there's a misprint in equation 10.1. 10.1 and 10.2. And 10.2. Okay. So here it is written Vi bar x. No, but I think it's Vi bar y here, summed over I. Okay. Yeah, that should be because it's this one. We want to cancel this, right? So okay, now you can see that. I mean, if you take the scalar product of this with any Vi Vj, let's say, then this gives you Vj bar. And let me put here j, because here I use the I. Okay. So when you take the scalar product of V with the Vi with this whole combination now, first term gives you that. That is what we calculated. Now the second term will give you, when you take the product, Vi bar x, Vj x times Wx integral, but that by definition is delta Ij. I mean, we have normalized it to delta Ij. So that and what is left over is simply delta Ij times V bar Jy, which becomes V bar Iy, and that cancels with them because of the minus sign. Basically, what this is actually a projection operator. This projects when you multiply this, when you apply this to anything, that basically projects it to the 0 mode space. Right? So you consider the full big space, the big space of the V's. Which satisfy these boundary conditions, right? And then when you apply this projection operator, it just projects onto the 0 mode space, subspace. So it's a projection operator. So this is the correct. I mean, this right-hand side now satisfies that condition, that this is orthogonal to the 0 modes of the L dagger operator. Okay. So now we should be able to find the Green's function. So this is, let me see, they have used a symbol G prime to indicate that this is a generalized Green's function, okay? Because you have modified the right-hand side. You have modified the right-hand side. Because, I mean, in some sense, you see, this is like the identity, right? After all, when you apply this on any function, right, and integrate it with the y, this just gives you back the original function, right? So this is like the identity operator on the space of functions, right? Now this one is a projection operator, which when it acts on the space of function, when I say it acts, meaning, so what is it? Maybe I should just explain that. I think although I did mention before, but so what do I mean by the statement that I take this operator and apply it on an arbitrary function v, right? So what it means is that I take this is some operator. Let's call it this depends on x and y, right? So what shall I call? Some operator fxy. So I apply this operator on any function y, a function which is subject to suitable boundary conditions and so on. I take this and integrate dy with the appropriate weight function. Okay, this is what I mean by applying that. So what do I get? When I apply the first term, the f is the sum of these two, right. So delta x minus y, the w cancels, so this will give you v of x, right, when you integrate. Whereas the second one precisely projects onto the 0 mode subspace, right. So so minus this projection operator, which is simply v bar j x and integral v bar j sorry vjx v bar j y vy dy wy. Okay. This will be some number. Once you integrate, it will be some number. So what it is going to give you is some linear combination of 0 modes. This is a projection. It projects out of this. It projects the 0 mode part. So this is the so that's what it's doing. This operator is basically a projection operator which removes from this v the 0 mode part, right. This is the full v, but now from that I am subtracting the 0 mode part which is contained inside. So it removes it. So it takes you out of the 0 mode space. This is what it's doing. Okay. So okay, this is fine, and exactly the same argument works for the L-dagger operator, right? Because for the L-dagger operator, if you consider such an equation equal to say some h, then just as before, the solution can only exist if h is orthogonal to the Lx 0 modes. L 0 modes, not L dagger 0 modes. So which means this h must be orthogonal to all the ui bar x hx. That should be equal to 0. Only then the condition. For the same reason, I mean, you just take the scalar product with the ui bar, right, and use the fact that this part is the same as Lx acting on the ui, the scalar product of v with the Lx acting on the ui. Right, complex conjugate, but then Lx acting on the ui are 0 because that's a 0 modes. So left hand side becomes 0, so therefore the right hand side must be also 0. So this is the necessary condition for that. And once again, we can modify the L-dagger Green's function equation. We were using small g, gxy, and again we'll use a prime to indicate that this is modified. So this will be wx minus, now I have to project this, I have to construct the projection operator which projects onto the 0 mode space here, right. So that is simply again normalizing it, find an orthonormal basis. So ujx u bar j y sum over j. Okay. So these are the two generalized Green's function equations. And now one can just proceed exactly like what we did before to construct the ordinary Green's function, and you will see that we can find a solution to that. However, this Green's function will not be unique, because you see, if I find a solution to this equation, a particular solution to this equation, to that I can always add any linear combination of the ui's, right. That will again, ui's are the ones which are annihilated by Lx. Lx acting on the ui's are 0, right. So given, if you give me one solution, then I can add to that any arbitrary combinations of the 0 modes, and that will still be a solution. So it is not a unique Green's function. Okay, that is the difference. But you can still you can use this to solve for the inhomogeneous equation, provided of course the right hand side satisfies the necessary conditions. Then you can solve. Okay. So let's see. So let me take an example and just work out. This is a very simple example again, just to see how you can actually construct this. So once again, let's look at the same equation, same example which we considered before. Say that my equation is very simple. This is equal to fx. This is the kind of equation we are looking at, and we want to construct the Green's function for this to be able to solve this equation. And the boundary conditions now, you see, before in the previous chapter, in previous section, the boundary condition we used was, I think, was it Dirichlet? I'm not sure. What did we use? Yeah, it was a Dirichlet boundary condition. See, we had previously we had used the boundary condition u at say one endpoint, equal to u at the second endpoint was equal to 0. I mean, the two endpoints was equal to 0, right? And this was Dirichlet boundary condition. And in that case, there was no 0 mode to this homogeneous equation. Because what are the two solutions of this? U1, one fundamental solution is U1 equal to 1, and other is U2 equal to x, right? And you see that there is no solution. I mean, no combination of this can satisfy this boundary condition, right? And that is why there was no 0 mode, and we could construct the ordinary Green's function. But suppose instead of choosing this, let me choose a periodic boundary condition. Okay. So, for example, I say that U0. Okay, here in the they have taken the interval a to minus a to a, but it doesn't matter. You know, you can just choose. I mean, let's keep the same. So we choose U0 equal to UA. Okay? Is a periodic boundary condition. At the two endpoints, the values of the U is the same, but this is only one boundary condition. We need two. We need two boundary conditions, right? So the second boundary condition, again, I take du by dx at x equal to 0 is equal to du by dx at x equal to a. So both the function and its derivative is periodic in the interval. I mean, at the two endpoints. So this is what's called the periodic boundary conditions. This was Dirichlet, and this is periodic.
Does it make any difference whether we put the bar on Vjx? I mean, it is, I think, the same.
Sorry.
Is there any difference whether we put the bar on Vjx?
Yeah, because it will not. Because I mean, in fact, it would not. I don't see how. Because let's see. I mean, the condition of this was that when I multiply this by v bar I x to this whole thing, right? That and integrate dx wx times whatever this whole thing is, okay? This whole thing, that should be equal to 0.
Yeah, sure. But we can switch this one by Vix, and then there we can. Yeah.
No, because I mean, this is I mean, let's go back to the language of the vector space. I mean, in this notation, the usual notation we are looking. So we had this equation, right? This was the equation. We had L U V, U active on F. But now I have to take the scalar product like that, right? Right? So this is basically what we are saying is that this guy, but this is actually V bar, not V. And it is this one which is by the usual condition of adjoint, definition of adjoint. It is simply U L dagger V complex conjugate, right?
Okay.
So that's and once you say that V is a 0 mode of L dagger, this vanishes, right? But the point here is that you have to multiply by U bar here, take the scalar product. Yeah. If you're going to multiply by U, you have to take the complex conjugate of this equation, because to write it another way, no? But then again, it will be the same thing. Once you take the complex conjugate, this will become bar and that will become n bar.
I say this because Vj bar is like a kind of Hermitian. So they live in the same vector space. So
But I mean, you see, not necessarily, no, because no, in general, you see, they could be. No, there is no reason in general that will happen. I mean, if say the L is in particular types of operators where all the coefficients are real and so on and so forth, then okay, those solutions will be real. Huh? But in general, they could be complex solutions, right? So just keep it general in a general situation, right? Yeah, in the real case, all these V's will be real, so it doesn't matter then. Okay, but just to keep it generally. Yeah. Yeah.
Can you give us some examples of physical problems that are zero modes?
I mean, yeah. In fact, I'm going to write this as an example, the Green's function, but this will still be real 0 modes. I mean, but maybe, but because I'm choosing a very simple differential operator where the coefficient here, okay, there is only one is real. But if you, in general, if you have this A, B, C, right? A times d2 by dx2 plus B times d by dx plus C. Because if A, B, C, you could choose complex functions, no? In that case, in general, the solutions will be complex. Right?
Okay, but yeah, I need the intuitive approach. I mean, that what kind of physical problems do we have differential equations such that the solution for the differential equation is like zero modes?
I mean, this is a physical problem again. You see, this is a problem where you are saying that so consider a free particle, right? So this is basically the free particle on moving in one dimension, right? This is the Schrodinger operator for the free particle because there's no potential energy.
Yes.
And you're considering the particle in a box with periodic boundary condition. So imagine you have a infinite potential, and the particle is, so this is 0 and A, and after 0 and A the potential becomes infinite. So particle is entirely restricted here, right? So then you will have periodic boundary condition at the two endpoints, right? Or not even that. I mean, maybe this kind of boundary conditions appear in more generally in a kind of a situation where you have a lattice type of situations. Okay, periodic boundary conditions appear in the lattice kind of situation. You have, so there's a translational invariance by discrete thing. So you expect all your wave functions to be periodic, right? Or if you think of x as an angle, 0 to 2 pi, right? Then again it should be periodic. So those kinds of situations appear. In the infinite potential well, actually you should have the Dirichlet boundary condition there, because you would expect that to vanish once, right? So not for the infinite potential well, but periodic systems like lattice, and so one-dimensional lattice, right? So this appears. Periodic boundary conditions appear. All the angular variables, for example, that's if you instead of x you think of theta or phi or something like that. No? Okay. So now. I mean, this is very simple examples, but I mean, this is in quantum mechanics, right? I mean, try to give you a quantum mechanics, but in quantum field theory, this plays a very, very important role. The notion of zero modes. Yeah, I mean, it's very, very important role. So okay, fine. So now, so let's go back and see. So is there a solution? I mean, any solution is of course a linear combination of these two, right? So an arbitrary solution U would be some alpha plus beta x, right? Alpha times U1 plus beta times U2. And let's see if they can satisfy this equation. So U0 at U0 equal to UA. So the first equation tells me that alpha, because at x equal to 0, this is 0, equal to alpha plus beta times A, right? First equation. So that tells me that, okay, alpha cancels, this implies beta is 0, right? So therefore I can now look at it. So the U is simply the constant. So this satisfies the first equation, right? Second equation is automatic, sorry, this equation, forget that, not that. We are looking at this periodic boundary condition. The second equation automatically satisfies because du by dx is anyway 0. Once beta is 0, this alpha is constant, so du by dx is 0, so that's trivially satisfied. So the constant, this one, U1 equal to 1, is a 0 mode, which satisfies this periodic boundary conditions. Not the U2, but U1 is a 0 mode. But now we want to normalize it. Let's again choose the weight function W is equal to 1. Like before, in the previous example also we chose W equal to 1. Okay. So let's choose W equal to 1, and we just normalize this. So normalization condition is simply, so let's suppose this U equal to alpha is the solution which is normalized, 0 mode solution. Then we should have dx alpha mod square, okay, with W equal to 1. The integral from 0 to A must be equal to 1, right? Alpha is a constant, so I can take it out. So this alpha square times A is 1. So I can just choose alpha equal to 1 over root A.
We drop out the phase.
It doesn't matter. I mean, yeah, it doesn't matter. I mean, this is again a real, it's all real equation. So one can just restrict to real solutions. Okay, so. Okay. So then we can plug it in. So what is the differential equation we are looking for? This is, of course, this is a Hermitian operator. I mean, and in fact, you can show that also. I mean, this is a self-adjoint operator, right, with the weight function 1. Okay, this we already discussed before. But you can also show that this boundary condition is also self-adjoint. Okay, you can just do a little bit of work and you can show that the for the L dagger also, you have L dagger is the same as L, and not only that, the same, if you choose the same boundary conditions for the V, okay, then the surface terms drop out. Okay. So this is also self-adjoint boundary conditions. Fine. So then the equation simply becomes, so the same, so the U is this, and V is also the same. So U is 1 over root A, V is also 1 over root A, because the fact that it is a Hermitian operator. So now let's look at Lx, G prime of xy equal to delta x minus y minus, I have to remove the 0 mode part. So there is a 1 over A, because is a V bar times V, right? So this will be actually in fact it would be V bar, sorry, what was it, V of x, V bar of y. I mean, there's only one 0 mode, so I don't need to put an index I. Only one 0 mode. Now these are they are constant, so it does not depend on x and y, and it simply is 1 over root A, 1 over root A. So this is simply 1 over A. Okay. In the notes, they have taken the interval from minus A to plus A, okay, instead of 0 to A. So then this will become minus A to plus A. So this integral will give you 2A. So the normalization will be 1 over root 2A. So that's only, but I just kept the same. I mean, it doesn't matter what interval you choose. So this is the equation we're looking for. Okay, so let's proceed exactly the same way. Yeah, let me see. Yeah, one second, just 1 second. Solution. Right. So you see, sorry, go ahead. You have a question? Somebody? Yeah.
I didn't understand clearly why you say that U1 is a only 0 mode there.
U2 is not a 0 mode because U2 doesn't satisfy this boundary condition. We said that, I mean, a most general solution is alpha U1 plus beta U2, right? So substitute that. So U1 is 1, so alpha times 1 plus beta times x, right? This is the most general solution. But now of this equation. But now we have to still satisfy the boundary conditions, right? So let's look at the first boundary condition. So let me call this is U. So what that says is that U of 0 equal to U at A. So this is U, right? So this left hand side is simply alpha because x equal to 0, this drops out. Right hand side on the other hand is alpha plus beta times A, correct? So this implies the beta must be 0. So beta must be 0, right? So there's only one 0 mode, which is the proportional to U1. Okay. So now you see that here, I mean, so far what we were doing is that we were just writing this, I mean, the Green's function we were able to, when x is not equal to y, in the absence of that, this would be 0, right? Like for the usual ordinary Green's function, there was no such term, right? You just delta function. But for x not equal to y, that would be 0. And then you can, so that's how we know that this must be linear combination of the fundamental set of solutions, right? But now it is not the case, because even when x is not equal to y, even though this is 0, that is not 0, right? So I need to, but on the other hand, this is very simple to solve for something, right? I mean, if I choose anything which goes like, let's say x square by 2a, right? See, if you apply this differential operator, Lx is this thing, d2 by dx2. If you apply that, d2 by dx2 on this object, you find that this is equal to 2x, 2 cancel, so it's just 1 over a, right? With a minus sign. So I can write the Green's function, g prime of xy is minus x square over 2a plus something which will satisfy the equation without this, right? So plus, I don't know, let's call it g tilde, something. I mean, let's write it like this. and then plug that back here, then you see that G tilde satisfies the equation G tilde xy is simply delta x minus y, right, because that term drops off. This term cancels that term. So now G tilde, of course, I can expand in terms of the fundamental set of solutions when x is not equal to y. So we write down the two things. So G tilde of xy equal to, say, C1 u1 plus C2 u2 for x say less than y. I mean always within the interval 0 to a. So here is my 0 a and here is some y. So in this region I choose that, and d1 u1 plus d2 u2 in the region, in this region, okay, x greater than y. Like this is the usual, so I'm going a bit fast. I mean, like what we did already last time for the ordinary differential ordinary Green's function. Okay. So now G tilde must satisfy the same discontinuity condition, because this satisfies the same differential equation like what we did discuss before, right? And from this equation we found that it must satisfy some continuity and discontinuity equation. Continuity for the function itself and discontinuity for the first derivative, right? So we see that, so we are saying that G tilde of xy as x goes to y plus should be the same as G tilde of xy as x goes to y minus. From the left or the right as you come, it should be the same value. So that tells me, that equation gives me that C1 u1 plus, so u1, let me substitute that, because u1 was 1 and u2 was x, right? So C1 plus C2x, I mean, so what is the u1, remember, is 1 and u2 is x, okay? So C1 plus C2 times x, but x is y, right? That is equal to d1 plus d2, again y. So that's one equation. So this implies that C1 minus d1 is equal to minus C2 minus d2y. That's one equation. Then the derivative, the equation would be dg tilde over dx as x goes to y plus minus dg tilde over dx as x goes to y minus. That should be equal to 1 over a times the, sorry, this a is interval. I mean that a was the coefficient of the second order differential thing, but that is 1 for us, right? And w is also 1. So this is simply 1 for this equation. So let's do this. So dg by dx, it simply gives you, because u1 is constant, so the derivative kills it. So and u2 is x, so the derivative just gives you 1, so c2. So this is c2 and that is d2. So it says c2 minus d2 is 1. So let's plug it back here. So that tells me that c1 minus d1 is equal to minus y. Okay. So we have determined, say, c1 and c2 in terms of d1 and d2. Now how do we determine d1 and d2? That was, you know, the whole thing, but so far we have not talked about boundary condition. Now I have to worry about the boundary condition. Okay. So far we only satisfy the continuity discontinuity equations. Okay. Now we have to plug it in, plug the whole thing. It's not just g tilde, is a g which g prime which has satisfied the boundary conditions, which means including that, right? And that is a crucial thing. That's a crucial thing. You see, without that there will be no solution of that equation. I mean g tilde, we know already that there is no ordinary Green's function. I mean, if there was a solution with g tilde satisfying the correct boundary conditions, then we would have said there is an ordinary Green's function, correct? So this will play an important role in the boundary condition when we study the boundary condition. So let's see. Again, let's try to. So maybe I can just write down then. So what is g prime of xy? G prime of xy is in the two regions is minus x square over 2a plus c1. C1 is, let's say, d1 minus y. D1 minus y. I will write everything in terms of d1. D1 minus y, and c2 is 1 plus d2. 1 plus d2 times x, right, because C2 times u2 is x. So this is the region where x is less than y, in this region. And the other region is minus x square over 2a plus d1 plus d2 x. Okay, this is for x greater than y. That's what we found so far. I mean, I just use the fact that G tilde satisfies those equations, and then there is a G prime has an extra piece here. This is continuous. There's no discontinuity here, right? This is continuous object. And now let's look at the boundary condition. So we want G prime at the first boundary condition was G prime at 0 y should be equal to G prime at a y. Correct? That was a periodicity. And the second equation was a derivative dg prime over dx at x equal to 0. It should be equal to dg prime over dx at x equal to a. These were the two conditions, right? So let's look at the first one. Now this is x equal to 0. So this is in this region, x less than y, right? So we should write it here now. So this one is simply, I have to just put x equal to 0 here, right, in this solution. So you get here d1 minus y, because these two terms drop out. That should be equal to g prime at x equal to a y, but x equal to a is here, so it's in this region. So we should look at this solution, and I put x equal to a there. So this gives you a square over 2a, so minus a by 2 from there. Then you have plus d1 plus d2a. So this is one condition. Then this derivative, so dg prime over dx at x equal to 0, I must use this. So you get here minus 2x over 2a, but x equal to 0, that drops out. So there is no such term there. And the derivative hitting here gives you 1 plus d2. So 1 plus d2 equal to this derivative now at x equal to a. So this gives you 2x, x equal to a, so this becomes 1. So minus 1 from there, and this derivative gives me plus d2. Okay, no, this something has gone wrong here. What happened? Huh? No, the derivative. No, g prime. So I must have made a mistake somewhere before. What was the equation? d1 minus d2 was equal to 1, was it? d1 minus d2. So we substituted d1. No, c2 minus d2 was 1. This is correct, right? C2 minus d2. So therefore C2 is 1 plus d2. So what's going wrong here? It is 1, right? Is it 1 or? Let's see. I must have made some silly algebraic mistake there. Discontinuity C2 minus D2 is minus 1. So why is minus 1 here? What is the discontinuity condition? Is there a minus sign there? Properties of Green's function. Maybe I made a mistake here. Yeah, correct, right? Because the equation, no, this must be minus 1. The equation was dg by dx as x g tilde, x goes to y plus minus, yeah, minus dg tilde over dx at x goes to y minus. This was equal to 1. Okay. So that would say this is d2 minus c2. I mean, I wrote it c2 minus d2 because In the y plus region, it's the second part, right? This part of the solution. So you'll get d2 minus c2 equal to 1. So this implies that d2 minus c2 equal to 1. So c2 is d2 minus 1, right? So this is d2 minus 1 actually. I hope there was no mistake there. No, but that was just a continuity condition. So that was g equal to that, so it doesn't matter which way. So I think this was probably correct. So d2 minus 1. So this is an identity, you see, because now d2 minus 1 equal to d2 minus 1. This doesn't give you anything. Okay? Second equation doesn't give you anything. And the first equation you can solve for, say, for example, d1. I know d1 also cancels here. So I hope there is no mistake here. So this tells you d2a. I mean, we can check at the end whether this is correct or not. d2 so equal to, you take that on the other side, so equal to a minus 2y divided by a. Okay. And d1 is free. d1 can be chosen anything. Okay. Now you understand why, because look at the coefficient of d1. See, d1 is multiplying 1 constant, the u1, but u1 was a 0 mode, remember? And we said that there is always, the Green's function is not unique. You can, given it some solution, you can always add to it any number times the 0 mode. That will still be a solution. That's why d1 is arbitrary. Okay. So this is always the case. You'll have two, see, to begin with you have 4 conditions: the continuity condition, discontinuity condition, and the 2 boundary conditions. So normally you would say with these 4 conditions I should be able to fix C1, C2, D1 and D2, right? But here we find that out of these 4 conditions only 3 give you non-trivial information. 1 condition was automatically satisfied. So out of the 4 only 3 are independent conditions. 1 condition becomes trivial. So that you can determine 3 coefficients, but 1 coefficient is unknown, undetermined. And that coefficient will be the one which multiplies the 0 mode. Okay. So in this case it was very simple because 0 mode was 1, it was one of the fundamental solution we chose, so it's just that d1 coefficient. Okay. And okay, d2 is this, you can plug that in here and that gives you the Green's function. You see, again, it was crucial. This object played a crucial role in this boundary conditions. This didn't play any role in the continuity discontinuity equation because this object is continuous anyway. Both its the function itself and its derivative are continuous, so they will not enter in the equation. So those equations, in those equations they don't enter, but they enter in the boundary condition. You see, and in fact you can see. Let's see, in the first boundary condition, I think it didn't enter, did it? No, it did enter. Yeah, this one. Yeah, but okay, this is something. This gives you. So I mean, let's see. Where are these terms? This term came here. Is that no? Yeah, it came here. There is one term. This came from there, and in the second equation. Second equation minus 1 here. Yeah, these 2. Okay, here it appeared, okay, it didn't matter. I mean, if this was not there, okay, the solution for D2 would be just this equal to that. Huh? But if this had not been there, there will be a contradiction, you see, because D2 cancels and minus 1 equal to 0. Right? That is why without this piece, without this extra piece which came from that extra correction in modification of the equation, that's where it came from. Right? So if this was not there, then there will be no solution. It will be inconsistent because this says that minus 1 equal to 0, right? So that again, just to illustrate to you that it was crucial to put this extra piece. I mean, which we knew anyway. Without adding this piece, there would have been no solution of this equation, right? But I mean, you see it explicitly here how that's working. Okay. So that is a way to construct. Yeah, so it's the generalized Green's function, and then again you can use this to compute.
Maybe we see the effect of this equation over A because of the boundary. I think the letter A. Maybe if we rearrange so that like from minus A over 2 to A over 2, maybe we don't see the effect there.
Oh, in the first equation,
Yeah.
maybe, yeah, probably, yeah, correct.
Yeah.
Although,
Because we can have some symmetry around, like.
Well, you're saying, okay, if you take the range from
Minus A.
so suppose you do it from there, minus A by 2. So here you will get, this will drop out because it's quadratic. It will drop out, yeah. So this will not show up, but here it will still show, I think, right? Because first derivative becomes linear in x, which is odd for when you take sign change, right? So it will still show up here. So yeah, this that depends on the, yeah, exactly, correct. Yeah. So, but this was not crucial. You see, this didn't, whether this was there or not there, there's no inconsistency in the equation, right? You can just use this to determine D2, but the inconsistency is here. Okay, so now let's see. So finally, the last thing I wanted to say is about the inhomogeneous boundary conditions. Yeah. So sorry, going back to this. I mean, now if I have an equation for this this equation, well, so long as this f of x is orthogonal to the 0 mode, right? So which means the condition that we must satisfy on the f of x is that f of x times the 0 mode, but 0 mode is just a constant, right? So dx, w is 1. So this integral must vanish. That's a condition on fx. Whatever the form of f you choose, it must satisfy this condition. Otherwise, there will be no solution to that equation. Right? And in such a case, then you just plug, I mean, you can find the solution of u by taking g prime u of x equal to g prime xy f of y dy. W is 1, so this 0 to a, where g prime is given by that equation. And of course, to this again, for any solution you can again add the 0 mode. It doesn't change. Huh? So there is 0 mode is always an arbitrary thing here. Okay. So let's go back to the inhomogeneous boundary condition. That's the last topic in the Green's function. And then actually today I wanted to start the discussion on the power series solutions, because that's what's most useful actually. Okay, so suppose now you have an inhomogeneous boundary condition. This happens in many physics problems. I mean, you know, for example, you may have, let's say, you want to solve some, say, there is two say infinite plates, metal plates, let's say, conducting plates, and you may have a situation where say there is some potential difference, electrostatic potential difference. So maybe here the potential is 0, so I don't know what V, I don't know what you call V is equal to 0, and here V is something, V equal to some sigma, and then you want to find the you want to solve for the potential in between. Okay. That potential will satisfy a second order differential equation. Basically, this becomes a one-dimensional problem essentially. So this is almost identical. d2v by dx2 is equal to 0 because there is no charge inside in here. It's a you know, but with this boundary condition. So this will be inhomogeneous boundary condition, right? So this is useful in fact. I mean, so now what we are saying is that instead of choosing b1 u equal to 0, we choose something, v1 u equal to some constant, sigma 1, and B2u equal to sigma 2. And question is, how will we solve for this equation now? I mean, say, yeah, so let's see. So we want to now again solve for, in general, I mean, in general, the equation will be also inhomogeneous. So we want to solve for LXU equal to F. Say this is the equation we're looking for. So the idea is that even though we want to solve this equation for the inhomogeneous boundary condition, we can use the Green's function that we obtain with the homogeneous boundary condition and solve for this generalized this more complicated problem. Okay, so we will still use the Green's function for the homogeneous boundary conditions. Okay. So the Green's function gxy satisfies Lx gxy equal to delta x minus y. I will assume there are no zero modes now. Okay? I mean no zero modes, just the boundary conditions here. Okay. Wx, so no modification of this equation. So I have just that, and the boundary conditions that the G satisfies, gxy. Let me just write G. Huh? G satisfies this with respect to x as a function of x. This is equal to 0. So it's a homogeneous. Notice this, that's the important point. Huh? This homogeneous boundary condition. B2G equal to 0. And with respect to the second argument, y, with respect to y, it should satisfy the adjoint boundary conditions, right? So B1 tilde bar of G. So this is as a function of y. B1 tilde bar G equal to 0 and B2 tilde bar G equal to 0. This is because of this equation that G of xy, the adjoint Green's function is the same as G bar of yx, right? For this reason. And this satisfies the adjoint boundary conditions, right? So x is the second argument here. So for the second argument, capital G satisfies the adjoint bar conditions, adjoint complex conjugate adjoint conditions. Okay, so these are all homogeneous, but nevertheless, with using this Green's function, we can solve for this equation. Okay, that's the idea here. Okay, so let me write down the solution and show you. So, so remember how we found the solution of this equation. I mean, one way to do this was again use the. I mean, so without this, how did we do this? Without this, we said if you take this Green's identity, V Lx V bar Lx u integral dx w minus dx w u L dagger x v whole thing. This was some boundary terms, right? Boundary term, right? With of course, if u and v satisfy the adjoint boundary conditions, they will vanish, right? Okay. So this was the generalized Green's identity. But so when they satisfy this boundary condition, this is 0. And then what we did was we took v to be equal to g of xy. Okay. Yeah, v equal to g of xy, and u to be a solution of this equation Lxu equal to f. Okay. So when we applied that here, this L dagger acting on v just gives you delta function divided by w. So w cancels, and integrating delta function, this one simply becomes u of x, yeah, u of at y, right? Because this L dagger x acting on g little g x y is delta x minus y. divided by Wx. So use that, take V to be this and substitute that, you get delta x minus y, W cancels and you integrate, so that just gives you U at y. So that tells you that U at y, I mean if this was 0, you would say U at y is equal to simply this integral, where V bar is G bar xy and LXU is f. So you find it's just G bar, small g bar xy times f. But small g bar xy is the same as capital G yx, right, from that equation. So what we are saying is that therefore the solution is U at y is equal to integral capital G yx f of x. Okay, dx wx. That's how we obtained. However, now we have to worry about these boundary conditions, right? I mean, so now because U is not satisfying, I mean, why this boundary condition this dropped out? Because we assume that U and V satisfy the adjoint boundary conditions, right? Now, all of these Green's functions are satisfying the boundary conditions for homogeneous boundary conditions. So therefore it would not drop out, because U is not satisfying the homogeneous boundary condition. U is satisfying this boundary condition, right? So we have to examine this Q but a bit more carefully. So what was the Q? Well, Q was basically was linear in U and antilinear in V, right? So Q involved generically terms like this. Let me say generic terms of Q was something like this. There was U V bar plus du by dx V bar plus plus U dB bar by dx plus, I mean, with various coefficients, let's say A, B, C, some capital C and some capital D. Correct? That is the kind of boundary, that's the kind of boundary terms you will find. Yeah? Okay. So now if you use the this I mean, so we are using this G for the V, the V, and for the U, instead of using homogeneous boundary condition, we use this sigma 1 and sigma 2. Okay. The point here is that, I mean, I can get rid of, let's say, here I have, sorry, this is to be evaluated at the x, this Q, I mean, this is the form of the object, but these are going to be evaluated between the two endpoints, right? x1 and x0. This is the boundary terms, surface terms. The surface terms evaluated at the endpoints. Okay. This is the general form of the expression. The precise form of A, B, C, D will depend on the particular differential operator you are choosing and the particular weight function you are choosing. So they will depend in a complicated way on that. But the point I'm trying to say is that what will appear there? The value of the function U and the first derivative of the function U at the two endpoints, right? And similarly, the value of the function V or V bar and the first derivative of the function V bar at the endpoints. This is all what's going to happen, right? Okay. So that is what the content of this information, this thing is. Now the point here is that, so I mean, using these two boundary conditions, I can, as you are saying always, that we can eliminate. I mean, these boundary conditions also involve these both B1 and B2 involves what? Involves the value of U at x1 with again some coefficients, say x0, alpha plus beta du by dx at x0 plus gamma U at x1 plus delta du by dx at x1. This is one B1 condition, and B2 is equal to again the same thing with alpha primes. I mean, some different numbers. Okay, these are this form, right? These are the two boundary conditions. But using these two boundary conditions, so now what has happened? This is equal to now sigma 1, not 0. This is equal to sigma 2, right? With these new boundary conditions. Okay, but no matter what, even if it is there, I can always eliminate two of them, two of these quantities, There are 2 equations and 4 unknowns, right? 2 of these quantities in terms of the remaining 2 quantities, right? Okay, and sigma 1 and sigma 2. Okay, so when I plug that back here in this boundary term, you will imagine, okay, how can I? Okay, the value for the V I know, because V is a specific object, the Green's function, right? For this we know what is its the value at x naught, value at x1, the derivatives of the Green's function at x naught and x1. So those are known now, because I'm assuming that we have constructed the Green's function for the homogeneous boundary condition problem, right? So since we have constructed it, we know. So all these quantities we know. This guy, I mean, this, this, and this we know, because by assumption we have constructed already this Green's function. Okay, so that is done. So what is unknown here is u, the values of u and du by dx, basically value of u and du by dx at the endpoints. Okay, but this, using these 2 equations, I can eliminate 2 of them, 2 of the quantities in terms of the remaining 2, okay, and sigma 1 and sigma 2, right, and they will appear linearly. I mean, everything is going to appear linearly. These are linear equations. Okay, now, so you may say, well, this is going to be a problem, because, okay, true, sigma 1 and sigma 2 will appear, which is fine, that we expect anyway, because, I mean, something must change after all, right? When I change the boundary condition, there must be some, I mean, the solution must change, right? That is part is fine. But what do I do with the remaining guys? So suppose I have eliminated these 2 in favor of those 2, right? So now this expression depends on this and that, and sigma 1 and sigma 2, right? But the point is that that should drop out anyway. Why? Because also for the homogeneous problem, where sigma 1 and sigma 2 are 0, these guys I can write in terms of that. Okay, but but in that case, you see, precisely we chose the adjoint boundary conditions for the V, so that those terms cancel, right? That is how we constructed the boundary conditions for the V, adjoint boundary conditions, right? So these will not appear, right? And what will appear is only sigma 1 and sigma 2. So ultimately, what is the, so the upshot of this is that right hand side is is completely determined by this Green's function g, or which is equivalent to the g bar, I mean, this one. So its value and its derivatives at the endpoints. But this is, we assume that this is, we have constructed already, we know it. And what else it can depend on? Only on sigma 1 and sigma 2. Right? So the problem can be completely solved using this procedure. So just again, maybe this looks a bit abstract. Let's again take a very simple example. Very simple example again of the same trivial differential equation. Yeah, I mean the equation which we had taken before, which is d2 u by dx2 equal to f of x. Okay, and again we don't want any 0 mode, so we will not use the periodic type of boundary condition. We will use the Dirichlet, say for example, Dirichlet boundary condition, but now with the inhomogeneous term. Okay, so u at 0, so say the x is between 0 to a, okay, and u at 0 we choose to be, let's say, sigma 1, and u at a equal to sigma 2. The 2 endpoints, at the 2 endpoints, for the before we had chosen this to be 0 0, right? Now we just put an inhomogeneous piece. Okay. You had some question? No. Okay. So okay, this is I want to solve this problem now. Okay, with these boundary conditions. So as we said before, we first look for the Green's function with the homogeneous boundary condition. But that we already constructed before in the last time, right? So we look for the Green's function for g x y with the homogeneous boundary conditions, which means just set sigma 1 and sigma 2 equal to 0, which is simply that the g at 0 y equal to 0 and g at a y equal to 0, right, to 2 boundary conditions. So these are the, so this satisfies the homogeneous boundary condition, and this we already constructed. This was, let me just not spend time on this again, just write down the solution which we did last time. Yeah, so it was, where is it? Here. It's difficult to find in this thing. Yeah, so the solution was, this Green's function we saw was g of xy was simply y minus a times x divided by a. This was for x less than y, and g of xy and equal to y times x minus a divided by a for x greater than y. This was the Green's function, which we constructed last time, subject to this boundary condition. Okay. But now let's use this to compute. So we need to know the surface term for this. What is the surface term for that? So if I plug in this here, so let's take v bar Lx, so d2 by dx2 u, started from there, and take the difference. So we get here, or maybe start from here. Okay, doesn't matter. Basically, you just obtain by partial integration, right? And w is 1, so there's nothing. So I just do a partial integration. So the one term you get, the boundary term you get is v bar d by dx u evaluated at the endpoint a and 0. Okay, and then the term you will get will be d by dx with a minus sign, d by dx v bar times d by dx v bar u. Then I do one more partial integration by parts. So I will get here minus dv bar by dx times u evaluated at a and 0. And after that, what I will get is simply dx u d2 by dx2 v bar. That's what. Now if I plug v equal to little g xy, this is a Hermitian. You see that this is a Hermitian operator with also the Hermitian boundary conditions. I mean, just self-adjoint boundary conditions. So it will be the little g will be the same as capital G. I mean, this exchange. Yeah, this will just satisfy this equation. In fact, it will be the same. This will be equal to capital G x y. For this case only, not generally, just for this case. So I mean, it's not a general equation. But in any case, so you'll get from here this d2x, this is f. So the first term just gives you dx g bar xy, which is the same as g yx times f of x. This is 0 to a. And this one will give me minus u at y, because this satisfies the Green's function equation, delta function. So that's that. And that's equal to this quantity. So let's see what is that. So v bar is so what is v bar? This is g bar of xy, which is equal to gyx. Okay. So we just plugged it in here, gyx here, and compute this. I mean, there are several pieces now. I don't know what should I do. I mean, this must cancel. Okay, I think we should actually do it. In fact, yeah. So v bar. So this satisfies. So what is this is g bar of gy of x. So we have g yx. So y at a times du by dx at a at x equal to a minus gy 0. Okay, this was at a, so this is computing this d by dx u at 0. Okay, so that's one thing, and then minus dv bar, so minus d g bar as dg x yx at x equal to a times u at a. U at a is sigma 2, okay, and then you have plus dg by dx by x at x equal to 0 times sigma 1. That is what the right hand side is. So, let us see now what happens at x equal to a. So, this is unfortunately here I have exchanged. So, maybe I should exchange this thing because here y is the first argument. Okay. So, I mean yeah. So, sorry, we can use the second argument, but we have to keep remembering that. So, here this is the y and that is the x from this equation, right? So, this corresponds to so you see here, I mean just replace wherever you see x you replace by y, and wherever you see y you replace by x. Maybe that is better, and then we will have no confusion. Yeah. So, let me just write this equation for the exchanging the two. So, gyx. So what is this? Here this equation was when the first argument is smaller than the second argument, right? Which means with y is less than x, right? First argument is less than second argument. And in that case, you see that this is x minus a times y divided by a, and this is when the first argument is greater than second argument. So, y is greater than x, and you get here x y minus a over a. Okay. So let us see. So, here you see x is equal to a. So, we are in this situation because x is greater than y, correct? But at x equal to a, this vanishes. You see, no, sorry, here, this one, first one, this vanishes. Okay, so this guy is 0. Okay. Now look at this one here, gy 0. So this is in this situation, right? Because this argument is bigger than the other argument, second argument. So x is smaller than y. So we have this, and then we have to evaluate at x equal to 0, but this is 0 again. X equal to 0, this is 0, right? So this is 0. So you see, that's what I was trying to tell you. You see, when you look at this expression, you see that there is these things, and I don't know what these are. The boundary condition didn't tell me what they are, right? So if they had appeared, there would be a disaster. I mean, you wouldn't be able to solve the problem, right? But they drop out precisely because the adjoint boundary conditions were worked out in order to cancel that exactly, right? That's the reason why it's cancelling. I mean, if it was not cancelling, that would have meant I have made some mistake in this. It had to cancel, okay, which is okay. And then now let's look at these guys. We can again write down what it is. I take this derivative. This is the region where x, the second argument is, so we're looking at this part. Take derivative with respect to x. So that's simply y over a, right? And y over a, that's it, y over a. So this object is, first expression is, this is simply y over a times sigma 2, okay, is plus x. And then for this one, I have to use this expression, okay, and I take derivative with respect to x. So it's simply y minus a divided by a. So that's plus y minus a divided by a times sigma 1. So this is the answer. So therefore we conclude from we can get the whole thing. So this is equal to that. So therefore we have a u of y is equal to, I have to take it to the other side, this to bring it in this side, y divided by a sigma 2 minus y minus a divided by a sigma 1 plus this expression, this integral. F of x. Okay. So that gives you the solution. In the homogeneous, when sigma 1 and sigma 2 are 0, you had only uy was only equal to that, right? But now this is the extra pieces you get when you're in homogeneous space. Yeah. But I mean, the main thing I wanted to emphasize in the example, by giving the example, was this fact. You see, that this, I mean, if it had not vanished, there would have been disaster. You couldn't have solved the problem, right? But that is because, I mean, that even in the absence of sigma 1 and sigma 2, this would have been there, right? But precisely we are obtaining the boundary adjoint boundary conditions by demanding that this vanishes, right? So this had to happen. So that's the idea here. Okay, so this is the way you can solve. I mean, for example, for that electrostatic problem that I mentioned, they say two infinite plates with the, say, the potential on the one end is sigma 1 and the potential on the other end is sigma 2. Okay, equation would be this equation. This is a potential. Okay, electrostatic potential. The second derivative of that is equal to the charge density. But if suppose there is no charge density, F would be 0. In that case, the second term will not be there, and you are just end up with this solution. Okay, it was trivial. I mean, that was a trivial case. No? But this kind of thing also works for, I mean, say spherical shells or whatever. I mean, some surfaces where you know the potential is that something. You want to determine the electric field inside. No, okay, but then it won't be first order differential. I mean, one variable problem. It will be higher dimensional problem. So there will be partial derivatives. Okay, but in all those cases, there are such situations happen where you have inhomogeneous boundary conditions, and you want to. So by using Green's function, you can determine that. If you can construct the Green's function, that is. Okay, so now 12:30. So maybe I can just start the discussion on the power series expansion, because that will require. I mean, it will take many lectures now. This power series part. So let me just start the discussion and then. But is there any question here before I erase this blackboard? I mean, in fact, now we'll address the question I think some of you are asking always. What happens if this coefficient of the second order differential operator has zeros? No? I mean, how will you handle that? This a d2 by dx2, that a, if it has some zeros, what happens? So now, I mean, so far in all this discussion, I was assuming that a was not vanishing anywhere. Huh? But now we'll consider a more general case. And in fact, again, what we will do is we will consider now, instead of one real variable, we'll consider a complex plane, and the differential equation will be on a complex plane. So there will be complex variable now. So the complex variable z, and the second order differential equation we'll consider is something like this: az. Or in fact, let me divide by a throughout, so that coefficient of second order differential operator is simply 1 plus pz d by dz plus qz. Okay, this is the Lz. Let's say this is a differential operator. So this in the previous language I was writing a, b, and c. So this p is b divided by a. And this q is c divided by a. So if a had some 0, p will have some divergence. P and q will have some divergences. So we will consider all possibilities. Now, there's such a, I mean, the solution of this differential equation will turn out to be dependent very much on the singularity structures of p and q. So there will be. So we will call. I mean, so let's say, suppose p. So we will take p and q to be kind of analytic functions, meromorphic functions. Okay. So we'll only consider situations where p and q are are analytic functions with only almost everywhere except at some isolated points, except poles at some isolated points. So possibly you may have poles, but no more. I mean, and those poles should be at isolated points, not there shouldn't be any accumulation point and so on. So you will consider this situation. So they are analytic, meaning that they satisfy Cauchy-Riemann conditions, or I mean, or in a more loosely speaking, they don't depend on Z bar. Basically, that's what it means. They only depends on Z. But you can allow some singularities, okay, of this type, pole type singularity. So there is a classification now. So Z naught, I mean, regular points are the points such that P and Q are analytic in some neighborhood of that point, of that point. So for example, let's say you have Z naught is some point which is, if you call it a regular point, if in some neighborhood P and Q are analytic, they don't have any poles, just where everything is smooth, regular. That's why it's a regular point. And then you have singular points where P and Q may have poles. Both P and Q, or only one of them, if it has a pole, then it is a singular point. The second singular point where either P or Q or both have some poles. Now, there is actually a further classification. Actually, sorry, this is not called regular point here. It's in the book. It's called ordinary points. Okay, so let me write it's ordinary points. These are called ordinary points where the functions P and Q are analytic, and other points are singular points. But there are two types of singularities. The reason of this distinction is that the solutions are very different for those two types of singularities. One is called so regular singular point. So so this has two classifications, two classes. Regular singular point, and irregular singular point. Okay. So regular singular point is the one where P has at most first order pole, and Q has at most second order. That is the okay. So this is the worst. I mean, so any point where which satisfies this condition, that the P has at most first order pole and Q has at most second order pole, you call it a regular singular point. Okay, the fact that it's a singular point says that at least one of them must have a pole, P or Q must have a pole. But what it is saying is that the order of the pole cannot be greater than 1 for this here and cannot be greater than 2 for this Q. And otherwise, if this is not satisfied, then you say it's irregular singular point. So for example, if there is a point where P has a second order pole or Q has a third order pole, you say that that's an irregular point, irregular singular point. The reason for this is that So in all of these cases, so we will not be studying this. Okay, this we will not study. We will be studying both these kinds of ordinary points and regular singular points. Okay, and we'll develop power series expansions, power series solutions for this. The reason why there's a big difference between these two. So, and I will just state the result, and I will maybe discuss it next time. I mean, we will show eventually, I mean, probably it will take me a couple of lectures to reach there, that in this case, I mean, actually, let's say, generally we'll have solutions of this type. There should be two solutions, of course, a second order differential equation, right? So as a fundamental set of solution, let's say. So U1 should be of the form, say, if I expand around some Z0, Z minus Z0 to some power R1, and then there is a power series n equal to 0 to infinity with some coefficient Cn Z minus Z0 to the n. And U2 will be also something Z minus Z0 to the power of R2, n equal to 0 to infinity, Cn, some other coefficients, let's say Dn, Z minus Z0 to the n. So if Z0 was an ordinary point, you will have an expansion like this, where R1 and R2 will be integers. Okay? So that it will have not even a branch cut. I mean, it will be completely smooth solution, analytic solution there. If Z0 is a regular singular point, it will turn out that you will have solutions of this type where either R1 or R2 or both perhaps may have maybe non-integer, so that there will be some branch cuts. And in some cases, there can also be some logarithm. Let me write it down. There's something like the U1. This is the U1 solution. U2. There can be also U1Z times log of Z minus Z0. Okay, some constant times this. There can be also this. That depends on detail. That depends on if the difference between R1 and R2 is an integer. If the difference between R1 and R2 is not an integer, this term doesn't appear. So, very generically, you have solutions of this type. When? For the regular singular point. So, if Z0 is a regular singular point, you would have either R1 or R2 or both of them would be non-integers, which signifies that at least one of the solutions will have branch cut. And in some cases, also some logarithmic branch cuts also appear. Some logarithms also appear. Irregular singular point, on the other hand, is a completely disaster, because there, if you try to expand this sum, at least for one of the solutions, the sum goes from minus infinity to plus infinity. So you have, this what we call horrible singularities, no? Because this goes Laurent expansion, it goes all the negative powers, no? So that's why we will not discuss irregular thing. We'll only discuss this regular singular point and that. Okay. So this is the next lecture I will be basically first looking at the ordinary point and show that in that case, of course, for the ordinary point there will be no log term, because log would be again singular at Z equal to Z0. We will show that both the fundamental solutions are analytic near Z equal to Z0 for ordinary points. And then we will show that for regular singular points, the solutions are of this type. The two solutions are of this type. Okay, this will be the main point here. I mean, power series solution, and then we'll go on to discuss some particular types of solutions, which are particular class of equations, which a particular choice of P and Q, which corresponds to whose solutions are this very famous, hypergeometric functions, which appear everywhere. So I will then start studying in detail hypergeometric functions. Yeah, I think there's no point in starting now discussion of that, because so we'll meet on Friday then.
Can we have some examples for those irregular singular points, differential equations? Yeah.
Maybe I will, if I get time, maybe I will go to, after doing the hypergeometric function, maybe I will go to some things called confluent hypergeometry. I've never been able to do that in all the previous years, because already by the time we finish hypergeometric function, it's already I mean 45 lectures, you know, this too much. This time I am going a bit faster, so maybe I would be able to discuss something about confluent hypergeometric function. So there would be, you will see situations where you have this irregular singular points. But I mean irregular singular points, I think if I remember correctly, those will appear at infinity. I mean, so now we will be always discussing the full complex plane plus infinity. So this Z0 could also be the infinity. So yeah, but and then there you will see that behavior near infinity would be horrible. I mean for those functions, the solutions. Right?